All right. Okay. Well, we'll talk importance sampling. Okay. So, do you guys remember this? We left off on Friday talking about this. We said we started off kind of with the notion of trying to evaluate an integral. Okay. So far, I feel like we've been dwelling on this topic for a long time. Okay. So we started off with like if we want to evaluate an integral, of some function, let's say h of x, then what we can do is from excuse me, thank you. If we want to evaluate an integral of a function h of x, what we do is we find the average value of h of x over a and b, and then we multiply a minus b times kind of the average value. Okay, and we're going to estimate the average value via Monte Carlo sampling. And then we said, we said, well, what if we want to estimate the expected value of a function over a distribution? Okay. So we said, what if we want estimate the expected value of a function h of x over some distribution f. Okay. And we said that this is the integral of h of x times f of x being the PDF dx, okay? And as long as we can draw values from the distribution f of x, then we can do Monte Carlo sampling to get an estimate of this thing, right? So we said the expectation over the distribution f of the quantity h of x is equal to this h of x times f of x dx. And we draw values from f of x to get the estimate there, okay? So, and then we estimate this. This is approximately equal to basically the average, the mean of h of x sub I, okay, where x sub I is drawn from the distribution f of x. Okay, let me just pause here. And do we understand this, or is this still like mystery that makes no sense? I don't know. Okay, your faces are not inspiring confidence in me. Um, okay, so the idea here is kind of the same idea as here, except over here when we were doing this, our proposal f of x was just the uniform distribution. Okay, our f of x was just the uniform here. Does 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 the intuition behind here make sense? Okay, yeah, I'm sorry. Um, I don't know how to fix that. I'm pointing at this part right up here. Okay, or in the upper part, the kind of the intuition behind here is like, what's the average value of this function? And I'm just going to just pick random values via Monte Carlo sampling. I'm just going to pick over here, I'm just sampling over the uniform distribution, and every single one of these can appear with equal probability. After doing this thousands of times, I've got, a bunch of these different values, and I take the average of them. And that's going to give me kind of the average value of this function here. Okay. Over here, we're saying, okay, what if I want the average of this function, except I'm not drawing from the uniform, but I'm going to draw from a different function f, okay? Something with a different density here. And what's the expected value of the function over that density, or over that distribution? We followed the same process, except now that I've changed my f of x, this thing, certain values will show up more frequently than other values. And so the expected value of the function still ends up being just the mean of my things that I've drawn via Monte Carlo sampling. Okay, just random. I'm just randomly drawing x's. This time the x's are coming from a different distribution f. Okay, is that okay? And because h of x and f of x are like we're multiplying things. Okay, we could if f of x is complicated, we could kind of just switch these around. Also, we could say, well, what's we could evaluate f of x, and we can just kind of treat these as different things. Okay. All right. Here's the thing is that this function, the distribution that we want, could be difficult. Right? We might want to draw from a different function, because f of x, the distribution of f of x could be difficult to deal with. Okay, so if the density f of x is complicated, okay, and that let's say it's difficult to draw values from f of x. Right. We spent a lot of time already talking about random variable, random number generation from like different distributions, and that was like what midterm 1 was all about, trying to draw values from some distribution with some arbitrary PDF. We can find like it's still hard to do that. Okay, so what do we do? What we can do is we can draw values from g of x instead. We can draw values from g of x instead. And so based on the difference between f of x and g of x, okay, g of x might produce some values a lot more frequently than what f of x would, right? And so to compensate for this, to compensate for drawing from the wrong distribution, in order to estimate the average value, to estimate kind of the expected value of f of the function, what we're going to do is we're going to take the expected value over the distribution g of the value of the function, but we multiply it by the kind of the ratio between the PDF of f and the PDF of g. Okay. So this is called the importance weight. This is used to correct for the fact that we are drawing from G instead of F. Okay. And so this is approximately equal to just the mean of, well, you take the h of your x sub I times the value of f at x sub I divided by the value of g at x sub I. Okay, and here your x sub i's are drawn, or x super I is drawn from the distribution g. So we just do this a whole bunch of times, and we take the mean of all of those values. All right, is this okay? And when we do this, we get, you know, it works out. Okay. So kind of the algorithm here is just, it's just applying this. Okay. So our algorithm for importance sampling. And again, sampling is kind of a misnomer in that we are not sampling from the distribution. It's just, you know, not really sampling. It's approximation. Okay, so kind of step 0 is pick a distribution g of x that, you know, hopefully resembles f of x. Because this will give you the best properties. Okay, if your g of x resembles your f of x, that's going to give you the best properties. I mean, technically your g of x could just be, you know, the uniform or something else, but if you do this, it's going to be better. Okay, all right, and then step 1 is just generate, you know, x sub 1, x sub 2, x super 2, you know, x super 3, all the way up through x super n, coming from the g distribution, right? So generate this from the g distribution, okay, and then use your x super I to calculate your importance weight. Weights, which we will define the weight, importance weight of x sub I, or x super I, is the ratio between f at that point and g at that point. So this basically says how often the thing should show up according to the f distribution, right? This is the density of f. So, you know, kind of density of f at x super I divided by density of G at x super I. Okay, and so the idea here is, how often how often x should show up under the distribution f, and how often it shows up under the distribution G. Okay. I'm trying to put as much conceptual stuff in here as I can. Okay, so how often this value xi shows up with f versus how often it shows up with G. Okay, so let's say you have let's say this is G and this is F. Okay, right here they're like the same. Okay, can you guys still see the green line there? Barely. Right here they're the same. So then, when you generate values under G, okay, it's going to show up with the same frequency. So there's no correction that needs to be done. Okay. Whereas right here, according to F, these values shouldn't show up super frequently, but with the G, they show up very frequently. Okay. And so to correct for that, we do F divided by G, and so this says, okay, because G is larger, this number shows this is going to be less than 1, and it corrects for our mistake here. Okay, and then so once we get these weights, so this is our weight at that point x of I, then we just take the mean. Take the mean of your weights times the value of the function at x of I. Okay? And so, we just average all of these things and we correct for the weight here. Okay, let's try a quick demo here with some code. All right, so here's our demo, okay, our example. All right, so imagine we have, we're going to call this the folded normal. Okay, so basically, it's just half of the normal distribution here. Okay, so this is basically half of the normal density. Okay, so our function f of x is going to be, because it's half and the whole area has to equal 1, it's going to be 2 times 1 over root 2 pi e to the negative x squared over 2. Okay. Okay, and this is for x greater than or equal to 0. Okay, and we want to, what is the mean? If this is our distribution, what is the mean of this? What is the mean of this function? Of this distribution. Okay, so we want the expected value of f of x, right? We just want the expected value over the distribution f of x. That's what we do. Okay, so in this case, it's effectively h of x is just x, right? When you're calculating the mean, so this becomes the integral of h of x times f of x. So this is the integral of x times f of x, and that's the expected value of a function, right? So this is what we want. We don't know how to draw from the folded normal. We'll just say that, okay? Or I mean, maybe we can figure it out, but we're gonna instead. So what we're gonna do is instead of drawing from f of x, we're gonna draw from a different distribution, g of x. Okay, so instead of drawing f of x, we draw from g of x. Okay, and then so g of x, we're going to use the exponential distribution. G of x will be exponential with lambda equal to 2. Okay, and this gives me 2e to the negative 2x. And so that thing looks like this. And it actually, okay, I'll just, so this is our folded normal, and this up here is our exponential with lambda equal to 2. All right, and it's okay that they cross over because it doesn't matter for importance sampling. It's for accept reject sampling, one has to always be taller. For importance sampling, it doesn't matter. All right, so we're going to use our exponent to generate random values. Random values x super I. Okay, so this is kind of my pseudo what we're gonna do. Okay, pseudo code or just kind of our list. So we're gonna use our exponential to generate values x of I. All right, and then we calculate our weights. We get weights. We get W by dividing. Basically, I can check. It's going to be f of x divided by g of x, right? So f of x is basically 2 times d norm, right? So I'm going to just do d norm x of I, right? Because it's just the normal density. And then I divide that by, what do I divide by? D exponential, right? D exponential of whatever my x of I is. This is okay? So this is going to be my weights. Okay? And then what do I get? My h is just x. So I'm going to find I'm going to calculate my vector of products. Okay? So I get a vector of products, which will be just x super I times my vector w, right? This because h of x, recall that it's really h of x times our w of x times our h of x. I guess I can rewrite it the other way. But h of x, because we're going for the mean, h of x is just x. So I'm going to just do x times w or w times x, okay? And so this is my vector of products. And then what do? I just take the mean of all of those values.
For h, it's the mean of what the random variable is?
Yeah, so here, the question is, what is the mean of this distribution? Okay, and so the mean of a distribution, the expected value of any of a distribution, the expected value of x is equal to x times the density of x, right? So, and if we're going to write it in the form of evaluating the function h of x over a certain density, this just means x is our h of x. Is that okay? All right. We're going to run out of time here, but that's okay. well, well, let's just try this. Okay, so I can just do, we're going to call it x. This is going to be r exponential. Let's do 1,000, and lambda is equal to 2. Right. So this is the exponential distribution. So my rate is equal to 2. And then my w's is going to be the ratio between 2 times d norm of x, and then I'm going to divide that by, what do we do? D exponential of x with rate equal to 2. So this will give me my weights, and then I take my products will be my x times my w, and then we take the mean of our products here. Okay, and this is kind of my estimate of the random normal. Now, folded random normal. Now, is that a good estimate? Let's see. If is there another way we can do this that that better illustrates how this works? Probably not right now. Let's see what I can demonstrate here. Mean of w times x. Yeah. Okay. Oh, I guess the theoretic value, the theoretic estimate should be square root of 2 over pi. I'm trying to recall where this is coming from. This is the theoretic value. So they end up kind of close. Let's just try 10,000, and yeah, those end up very, very close together in terms of trying to get the expected value of some function here. You know, when you do importance approximation, importance sampling, often you get improved performance versus using the uniform. Okay, we could have tried to do generate values using evaluating the function using the uniform, and the performance there will not be as good. So the you have the basics to do the last problem in homework 2. Okay, I mean, the importance sampling, the algorithm is very simple once you understand kind of conceptually. The hard part in homework 2 for that last problem is you got to figure out how to calculate the ratio between the desired PDF and the PDF you're using to generate your values, okay? Because the desired PDF in your homework is this complicated thing. So the hard part is dividing that desired PDF by the PDF that you want, okay? But I mean, you can just plug it into R and it'll do it for you. So you just plug in the PDF and whatnot, okay? All right, we'll talk on Friday too.